All right, time for another draftphysics.com, debatephysics.com also. Video presentation, so just a draft video. Okay, I was just doing some thinking. Yeah, I do a lot of that in spite of the critics. About how energy is transferred by objects, especially when objects are, say, an empty space and they radiate their heat. And the idea would be is, well, how do they do that if they don't have contact with anything that can leave with a momentum, right? I mean, the idea is if the heat is essentially a kind of momentum, the electrons and protons, and how can it give their momentum away? And it's sort of in that vein. So this is all completely has nothing to do with conventional physics. So just understand they don't believe any of these things to be true. So my argument is that electrons only move because bits of force stick to them. Okay, so a piece hits them, a little bit, and it sticks and pushes it. So the little bits of force have momentum, and they give the electron momentum. So this thing moving the speed of light hits an electron and moves it something much less, let's say 10% per little bit of crap that hits. So if a second one hits with nothing coming from the other way, that's the important part. So nothing's opposing it, and a second one hits and it collects two of them, then it would be going something like whatever 19% of the speed of light, and it's always 10% of whatever the speed differential is, so it can never go faster than the speed of light. And if a third bit hits, it collects it, and so now it has a velocity that's getting higher and higher. And so the idea is this is what's happening on the surface, okay, of a substance, is that the electrons are constantly being pushed by the pressure of electrons out, and then they go back in, they go out, they go back in, they go out, they go back in. Now the trick is, the argument is that if a force bit comes from the opposite direction, then this last bit just reflects. So it would reflect in the opposite direction. So the momentum of the bit essentially goes right through the object in a sense, okay? Except this one also reflects. So, you have two reflections. This gives away essentially its piece of its momentum, the pusher this way, and the object is rejected, which means it has to reflect. Don't know if you need to know all that to get the principle here. So the idea would be, is you could understand that these collected force bits have a very high frequency. You could argue an infinitely high frequency. All right, so if red light looked something like this in spacing, and blue light, you could argue, might be looking like that in terms of the spacing between impacts, and that's defining the frequency of the event that will be a photon. So the argument would be, is you can sort of see that the momentum going out is in this form of a very high frequency, and the momentum that'll take it back in, that is this energy. So let's just say this was infrared, okay, and that this was red, and then blue would be, something much closer together. But that's sort of the scale, is that the scale is a doubling in many cases. So, red light to blue light is essentially halving the number of nanometers. You go from 700 to 350. And you could argue that that scale just keeps going, through the spectrum in terms of creating a halving or a doubling of the frequency, a halving of the wavelength, for things that we start to create borders for, where we establish a line and say there's a line. Now the spectrum of infrared light would be many halvings, and then microwaves would be many more halvings. So there's lots of doublings of the intensity, you could argue, the frequency. All right, well, anyway, don't want to get too lost in that. But the simple argument is the out pressure is at a high velocity, okay, because you have bits that you're collected, they're both pushing at the same time, and the energy going in, okay, is at a much lower frequency. You'll be hit and go at a slower velocity, and then you might get hit by that second one and increase your velocity, but it's going to be a total average that's slower. So when it pushes out, it compresses the field so it can convert invisible light into visible light. And in the case of something hot, right, in the case of what I'm doing now, the light reflecting off me is light just being reflected. So, I'm not converting infrared into visible. I'm just taking visible light and reflecting it. So if you had a temperature differential, the idea would be the hotter it is, the higher the pressure, the more energy that's behind the electron when it moves. So it moves out with more energy and it goes back in with less energy. And that essentially, less velocity. And that essentially accounts for the energy transfer, because the pressure going in is essentially less than the pressure that went out. So you could sort of argue that 3 units of velocity tightly compacted, and what goes back to the environment is, a compression in the frequency that stops it from moving, and then it slowly goes back in. All right. And through the energy of the field, and the field is just the extra field that you went into. The energy was already heading for you, so it's going to hit you, and all you did was change the time that it hit you. So you're not changing how much energy is going in, you're just changing the timing of the energy going in. Yeah. So that differential, you can sort of understand that there's more velocity going out than velocity going back for the electron. And that's the differential that allows it to dissipate its extra pressure. It is not that it's not excreting force, it's just reflecting force. And it's reflecting it at a higher frequency, which is a consequence of a time differential of when it I hate to say how it stores the heat, but yes, you have to just think of it as all being heat in a way. I mean, all motion is just heat, and it's heat in one direction. But heat, motion of electrons, all of that is energy. Yeah. All right, let's see if I can restate this for clarification. All right, let's try this from a more conventional diagram of the atom. So the atom has got a net positive nucleus. Now, my distinction from the conventional theory would be, as I would make the argument, it's only net positive. It does have negative electrons in it, so it has a 2-to-1 ratio of protons to electrons, and it's net positive. And now the electrons in the outside will balance, to the equal number of electrons and protons. So the orbiting electrons, I'm arguing, aren't really orbiting. They're stuck in positions between opposing electron force, and the attractive force of a proton. So every proton has electrons on either side of it would be sort of the argument, or vice versa, however you want to look at it. And the fact is any attraction to a proton will come with some repulsion from electrons. So the interior electrons, so you could argue, well, let's just say there's only 4, just to make it simple. And this is only one-dimensional, so it cheats the argument a little, are under higher pressure and are closer to each other. And the further out electrons are under less pressure, and they're spread out based on where the other electrons are to maximize their distance from the other electrons and maximize their distance to the protons, to be as close as a proton and far away from electrons as possible. And so that's essentially another ring of pressure. So these electrons are in a different pressure. Okay, we'll just make them bigger than the interior electrons. All right. So, well, that's not the right place for an electron. I have to put them here, 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 and here. All right. And so on. So the next ones are even further out. They're further away from each other, and the pressure is lower. And so what's happening when a photon is being created is that an electron has the freedom of motion, okay, to go from being in this high pressure, right? Yeah, this one's the defect here. Okay, so it's under high pressure, and it goes to a place where there's low pressure. And then these equalize into a new position of 3 instead of 4. And so it just changes what's in the orbitals and their distance, and the subtle change in the amount of total pressure. So the total pressure in the interior goes down because you've ejected an electron. So that's an electron moving a big distance, is jumping how many levels from the interior pressure to the exterior pressure, and it's making that jump at a high velocity, is the argument. All right, so that's the nature of heat. Okay, is the fact that electrons are doing this process of moving or migrating from one level of pressure to another level of pressure. But they're also just oscillating. So especially the ones on the surface. So if you have a bunch of atoms, you could understand that the electrons are on the outside, and that they're going to tend to oscillate in and out of the surface, all right, based on how much heat is in the object. So the more heat, the more they oscillate. Okay, but it's not enough distance. They're not moving enough distance, all right, to increase the frequency of a force. So they have to move a bigger distance to take the frequency coming in and compress it. So they push a bigger distance, they hit more stuff, they compress that stuff in space, in a field of space. And so they convert infrared, say, into visible light merely by pushing into the field. And as they're pushing into the field, they're hitting those objects, slowing down and stopping, and then retracting. Yeah, so that fits. The change in the velocity is the tricky part. Obviously, they're not going to be perfect exchanges in frequency, and so that's why some of them will be visible photons, some of them won't, because the frequency won't be consistent enough, because they're slowing down as they're moving. And so if they're taking a perfect photon in, they're going to make an imperfect one out. But the catch is they can take imperfect photons coming in and make perfect photons coming out. So it works both ways. All right, that's a little better. So their physics thinks the high energy is the outside orbital, and the low energy is the inside. It's exactly the opposite. The high pressure is on the inside, and it's electrons moving from the inside to the outside that creates an increase in the field pressure, the pushing out pressure, what's excreted. And it's the pushing in, where you're taking an electron from the outside and push it into the inside. That's the one that takes energy away. That absorbs energy and puts the energy back in the atom, because it compresses, where there's 3 electrons, it makes it 4 again, and they're compressing, increasing the force, because there's 4 in the same space there was only 3 before. So obviously they're less comfortable, you could argue. All right. I hate that. Alright, so we'll try another way. So I was thinking maybe the electricity analogy is that you have a bunch of atoms that have equalized their tension between their electrons. So again, you do have to understand that it's just the tension between the electrons and their attraction to the protons on the inside that's holding the material, okay, together. And what you're doing when you're adding electricity is you're adding electrons, okay, and the point is you're adding them at a velocity. But either way, you're adding a volume of motion. And so when you're putting the pressure in, the voltage, it's essentially a pressure. Now you have to understand that there's two elements. You can have one electron moving fast, or you can have numerous electrons moving slow. And it's the same increase in the pressure you're creating in the vessel. So the vessel just cares about how much motion there is, okay, pushing on the electrons. So more motion means the electron has to move more, means there's more movement in the other electrons. And more electrons moving spreads also. Alright, so you're increasing the pressure, and the increase in the pressure has a couple of different consequences. So that sort of requires a different drawing. Okay, so one of the consequences, let's go back to the simple atom again and say this configuration. And say you're pushing an electron into this electron. This one's getting closer to this one. That increases the pressure and it pushes this electron this way. But that means these electrons have to be pushed out of the way. And so they're going to tend to move in some direction that's going to still have a component in that direction, but it's going to be, because they're pushing away from this electron, it's going to be a little bit crooked. And so that's your sort of right-hand rule, or your perpendicular rule, that the electricity goes this way and the magnetic field comes out this way. It's because the atoms are changing their shape. But it's not this motion that's creating the field, all right, because it's not enough motion. It's just the fact that you're changing the shape. You're changing atoms that were nonpolar into atoms that are polar, in the sense that you've moved electrons out. You've moved these two closer together, you move these two out, so you've changed the shape of the atom, and now it's a polar atom, essentially having two south poles and two north poles, you could argue. All right. So that explains the inductive part, okay, where now the energy that hits, okay, is seeing a different configuration of protons and electrons, so it's going to reflect a different pattern. And it's a pattern other magnetic objects can detect. Things that are magnetizable can detect by turning into also being polarized by the field. The field hits them and polarizes them. So you can understand if this energy goes out and it comes into this wire when there's no current in it, and it hits this wire, well, it's going to do exactly the opposite to the atoms. It's going to push them in exactly the opposite manner that just pushed them out by this electricity. And they're going to end up getting polarized in exactly the opposite direction. They're going to squeeze this way and spread that way, duplicating the electricity. So that's how you create the inductive part. And the heat part, okay. So back to this example. So if it hits straight on in between the nucleus, you can understand it's not going to convey the electricity very well. And so the electrons that are going to have a more likelihood of conveying the electricity are the electrons that aren't separated by the nucleus. So these electrons, when they're hit, they can push into each other and maintain a really straight line. So a percentage of the electricity, okay, it's not going to have a problem. Now the problem is once it starts getting hot, you can understand all of this is jiggling more. So everything's jiggling more, okay, in all directions. So the hotter it gets, the less effective you get in terms of putting, getting the pressure to move in that one direction. It starts moving in all these directions, and that's when you start radiating the pressure, because you're doing this quick, you're doing out quick and in slow, and so you're radiating or compression into the field, and you're going to increase the frequency of the stuff bouncing off this higher velocity that you're moving out, and then slowly back, yes, high, out, you know, that kind of thing. All right. Yeah, that still isn't quite. So you can understand that when you cool a wire, a conductor, that you've taken out all the jiggling part. So at least there's no, the electrons aren't doing this as you're trying to push them this way. So you can understand if it's moving this way and you hit it this way, then it's going to go this way instead of this way. So the colder it is, the straighter everything stays. All right. So that's why superconductors are more efficient, is because there's less noise in terms of the motion of the electrons. So it's the noise that's really a problem, the wrong direction part. And so the colder it is, the less likely it is there's an electron going the wrong direction. It's probably not the right way to say it. Going in randomized directions. And also defects, if there's any kind of defect in the conductor in terms of some sort of impurities, that'll make the wire, that'll make it hotter, because the impurities have a misalignment of the electrons, and so they're pushing not on another electron as evenly. And so there you have more reason for why the direction of the force changes. And it's really just about keeping the direction in the direction of the voltage. So the simple principle is the faster it's going, the more likely it is it's going to keep creating energy in the direction it's going. And the slower it's going, the more likely it is it's going to start spreading the energy in other directions. Yeah. And the advantage of slower, though, is that you involve a lot more atoms in the process, and that means you're changing more atoms into polar atoms, and that's why it gets more magnetism. Electromagnetism doesn't work with high voltages. It only works with low voltages because you need high amperage. You need to involve as many atoms as possible, so you're creating a whole bunch of little magnets, and a whole bunch of little magnets makes a big magnet. Simple enough. All right, so finishing up. So this is sort of like, you could argue, an oscillator. So you could think of like a pendulum, okay, oscillating at equilibrium. It's moving the same speed, okay, for the same distance, let's just say. And what's happening is you're changing the velocities when you're interacting with a field or with another object. You're taking pendulums that are at different rates, and they're banging into each other and changing the rate at which they are at the new equilibrium. So after the interaction, they'll exchange motion, because one of them has a fast motion out and a slow motion. I don't know how to draw that. It's the same distance, but it's going to do it over a larger period of time. So it takes less time to move the distance because it's at a high velocity, and then it's at a low velocity going back. So there's a time difference, and the time difference is essentially what you're exchanging, is the speed at which you're oscillating. I don't know exactly, because it's a broken oscillation when you're transferring or changing the field. So when everything's at equilibrium, you're basically, the stuff hitting you isn't changing your oscillator. All right, it's at the same rate, and when you impose a force, you're changing the oscillating rate and therefore expelling more energy than you, because you're getting more in. And how much of that you keep will be the exchange between two objects, will be how much of a change, whether you slowed one of them down and sped one of them up, essentially, in terms of the oscillation, which ends up being a reflection of how much pressure is inside of the material. So the pressure decides the rate at which there's a time difference between this motion and the pushback from the consistent, generally consistent universe. Okay, so when the universe isn't doing something, when you're not shooting a beam of light or doing something to change it, it's at an equilibrium. And then when you change the field, that changes the motion inside, increasing the pressure. And then that increase in pressure means you're going to, as soon as the field relaxes, you're going to expel that pressure. So as soon as something stops imposing heat, you start radiating the heat. Yeah. But if something's at a constant temperature, a high temperature, you can't get hotter than the temperature it's imposing. And the only way you can get hotter is it has to keep increasing, accelerating the temperature it's imposing. You could argue. But that's for a whole object collecting it. So obviously if you shoot a laser beam at a surface, and the surface can't transmit the heat, then all you're going to do is burn the atoms, and you just keep burning the atoms. So burning atoms is a different rule. You'll certainly be able to burn a hole right through the substance because you're breaking the atoms, not because you're breaking the atoms from the surface. You're not spreading the heat to the entire surface and creating an oscillation in the whole surface. So the point of impact will be a much higher temperature. All right. Anything else to say? But it's just like anything else. It's it always comes down to there's two components. There's a velocity component and a mass component, and they're both equal in terms of their capacity to create motion and action in the universe. All right, so we'll call that a video. Still sort of drafty. A lot of this is going to change. There's all kinds of extra added stuff you have to put in here, recognizing that protons and electrons are different. So the fact that they're going to have a relationship to each other that's inverse, meaning that their capacity to affect each other, and the idea is that energy that would affect an electron, when it hits a proton, it gets turned into proton energy, and the proton energy goes through the electron and comes out electron energy. So you can understand that the electrons are constantly pumping invisible force into electrons, and it's coming out as electron force. So there's all kinds of places you can understand inside the atomic structure where there's all kinds of places where a boost in motion can be created by just merely moving an electron in front of a proton. So the electron here would be radiating a certain amount of electron pressure, but if I move it in front of a proton, the proton force is now going to be converted into electron force. So now the electron's going to radiate more electron force because it's converting the proton force into electron force. Boy, I didn't realize the pink shows up so well. Interesting. Anyway, okay, so that's enough of a video. So till the next time and such, so forth and whatnot. I probably should state that I did HTTPS, the website, I think, successfully. So it should now not, the people who have a problem with the website because it's not secure and all that crap, that irrelevant crap that the internet created for no good reason. I mean, encrypting data from a website that doesn't have any need for secure data is just a waste of encryption, frankly. And it can't be can't be the best option. So in my opinion, it's a pretty poor for the internet to worry about security on websites that don't solicit any personal information. But anyway, it's the way of the world, and they all turn it into some other racket to charge people for no good reason. And that's the irritating part. But anyway, for the few complainers, at least that should solve your website bullshit complaint problems. We'll see. Probably some new issue. But anyway, till the next time and such and so forth and whatnot. Yeah.